Okay, so let's start the last session of the IGST 2020 conference. New developments with the talk of Yifei He from Saclay and Paris, who is going to talk about geometrical four-point functions in the 2D critical Q states, Q-state POTS model.
Okay,
so,
thank you. Okay, thank you. I want to first thank the organizers for giving me this nice opportunity to talk here, especially since what I'm going to talk about is not directly related to gauge theory or string theory, but I hope my talk can give some interesting perspectives on exactly solvable models. So since the subject is probably not familiar to everyone, my talk is not going to be very technical. I will just focus on summarizing the main ideas and presenting the results. So the title is Geometrical Four-Point Functions in the 2D Critical Q-State POTS Model. It's based on these two recent papers. The first one together with Linnea Grant-Samuelson, Jasper Jacobson, and Yifei He, where we made some interesting connections between the POTS model and the minimal models. And the second one is this one together with Jasper Jacobson and Yifei He, where we use conformal bootstrap to determine the four-point functions in the POTS model. So I will start with a brief introduction of the POTS model and its geometrical correlations, as well as the CFT content. And the goal is to determine the four-point geometrical correlations, which we are going to use the bootstrap. But before doing that, we will make a small detour to make some connections between the POTS model and the minimal models. And in the end, I will give a summary. The POTS model is defined on a lattice where at each side there's a spin variable taking Q different values, and between the neighbors there's a ferromagnetic interaction. So with this, we can write down the partition function in this way, and we sum over all the spin configurations. And this is well defined for integer values of Q larger than or equal to 2, and we recognize for Q equals to 2, we have the familiar Ising model. And on the lattice, when the neighbors have the same spin value, they form a bond. And so each spin configuration can be seen as a configuration of such bonds. And the connected components of these bonds are called the FK clusters. So for the partition function, we can then rewrite it in terms of these clusters, such that we sum over configurations of the clusters. And in this way, this quantity Q enter this configuration in terms of the clusters only as a parameter. So the model is analytic continued to real values of Q. And in particular, for the limit Q goes to 1, it describes the percolation problem. And on two-dimensional square lattice, for this parameter V here, taking the critical value square root of Q, for Q between 0 and 4, there is a continuous phase transition, which is described by a CFT. And there's an equivalent description of the model, which is through the loops. Suppose we start with a cluster configuration, then we can take the midpoint of each plaquette and connect the dots to form the loops in such a way that they bounce off the clusters. This way, each cluster configuration is equivalent to a loop configuration. So we can also rewrite the partition function in terms of summing over loops, which takes this form at criticality. And from here, we see that each configuration, one loop contribute to a weight of square root of Q. And then we can talk about correlation functions. The most natural correlation function to discuss is the spin correlator on the lattice, where the spin variable is defined in this way. But this is only well defined for integer values of Q. So a more generic correlation function is this kind of so-called geometrical correlations, which are defined in terms of these clusters. And we're going to take a 5-point function as an example to explain. So suppose we have 5 points on the lattice, and then we can calculate the probability such that point 1 to 5 belongs to one cluster called A, and then point 3 belongs to a different cluster, which we label by B, and point 4 belongs to another cluster, which we label by C. And then outside these clusters, there can be arbitrary configurations that we sum over. And such kind of probability quantity is what we call the geometrical correlations. And important thing is that this is well defined for arbitrary real values of Q. And we're going to focus on the 4-point geometrical functions, which includes these 4 kinds. The first one is when all 4 points belongs to one big cluster, which we call PAAAA. And second one for 1.13 belongs to one cluster, and 2,4 belongs to a different cluster, which we're going to call PABAB. And then the rest is similar. And the goal is to determine these most fundamental 4-point functions in the POTS CFT. So for Q between 0 and 4, there's a CFT describing the continuous phase transition. And we can parameterize this Q variable in this way, where the X takes continuous values from 1 to infinity. Then the central charge of the corresponding CFT is given by such expression, which takes continuous values from -2 to 1. And from here, we see that the POTS CFT is in general non-unitary. It's in fact, as we have understand now, logarithmic. And for the fields in the CFT, we can use the calc parameterization like in minimal models and write the conformal weight with the 2 indices R and S. And but in the case of the POTS model, these indices can be fractions. So the fields are in general non-degenerate. And this kind of non-degeneracy and the non-unitarity are the main challenges for solving the model. And in this notation, the order parameter, which is the spin operator, takes this indices 1/2 and 0. And we will focus on the 4-point function of this spin operator when we're going to use bootstrap to determine it. And these 4-point function decompose exactly in terms of these 4 probability quantities that we just talked about. So the first step is to understand the spectrum. And since the 4-point function of the spin operator in the CFT can be expanded using the conformal blocks, the coefficients here, which we're going to call the amplitudes, comes from the OP coefficient square. And depending on which of these 4-point functions that we talk about, the spectrum involved, it will be different. And also the amplitude will be different, which we are going to label accordingly. So the spectrum here was recently found in this paper. They are given by representations of the affine temporally leap algebra, which is an algebra describing the loops of the POTS model, which are generated by some elements on the lattice with their algebraic relation. And each of this module, we're going to label it with this W. And each module contains a tower of conformal primaries and descendants. And their conformal weights, we can read it using the labels of the affine temporally leap modules. And depending on which of these 4-point functions we discuss, different combinations of such modules will enter their spectrum. And one important piece of information is that there are some degenerate fields in the POTS spectrum, which we're going to use later. So to give an idea, I plot here the total conformal dimension versus this parameter Q. And the blue here is this very dense spectrum for these 4-point function that's found in this paper. And in comparison, for red, it's a minimal model spectrum. Analytic continue to generic values of central charge that covers the whole range of Q between 0 and 4, which is a very simple spectrum covering a subset of the POTS spectrum. So why are we interested in this comparison between the POTS model and the minimal models? It's motivated by this recent work here. These authors considered a 4-point function of an operator whose conformal dimension coincide with the POTS Potts spin operator. And then using constraints from crossing, which is a conformal bootstrap philosophy, they find a spectrum of this 4-point function in the OPE, which is this simple spectrum that I just plotted. And then by comparing with Monte Carlo simulation, they find that this gives a very good description of these combinations of the Potts probabilities. But then it was understood later that the 4-point functions here is not the Potts 4-point function, but instead an analytic continuation of the type D minimal models to a generic value of central charge. Or one can think of it as a non-diagonal generalization of the C less than 1 Liouville theory. So it was quite curious why a 4-point function of analytic continuation of minimal models can give a good description of the Potts probabilities. So to understand this, we use the RSOS lattice model. The continuum limit of this model is known to give rise to the minimal models. And the advantage of using this lattice description is that in this model, there's a natural formulation in terms of these clusters and loops, very similar to the case of Potts model. So correlation functions can be written in terms of sum over diagrams of such cluster configurations. And then we can use this to write this 4-point function and compare with this. So what we found is we focus on this 4-point function considered by these authors, and we find that it's given exactly by this kind of Potts cluster configurations, but the quantities are not exactly the same. The first term is precisely the Potts probability PAAAA, and the second term, which we call a pseudo probability, is not this, but it's a sum over of cluster configurations with 0.13 belongs to one cluster and 2,4 belongs to a different cluster. But for the loops surrounding these clusters, their weight is not the usual Potts weight, but some other non-trivial values. But the difference between this pseudo probability and this expression using the Potts probability involves some highly unlikely configurations. So it will be hard for Monte Carlo to detect such difference. And one interesting thing is that using the numerical technique that was used to determine the Potts spectrum of these 4-point functions, we can also find the spectrum of these pseudo probabilities which appear in minimal models. And we find that they involve almost the same conformal fields as the Potts probabilities, but with some different amplitudes. And we also find some really amazing facts on the lattice about how these fields contribute to these two different quantities. So first, if a conformal field appear both in the Potts probability P and pseudo probability P tilde with the same kind of geometry like ABAB, for example, then the ratio of their amplitudes depend only on which affine temporally leap module this field belongs to and the parameter Q. And second, if we have a conformal field appearing in different Potts probabilities, then the ratio of their amplitudes depend only on this module W also and the parameter Q. And from the lattice perspective, these kind of ratios do not depend on the lattice size. So they carry to the continuum limit and still hold in the CFT. And we managed to extract many of such ratios, and they are given by rational functions in Q. But for the moment, we don't know how to derive them from a first principle. But the fact that such ratio exists tells us something important about the Potts model. Suppose we compare two different quantities. One is this Potts probability, P, ABAB, and the other one is this pseudo probability, P tilde ABAB. These two quantities are related on the lattice by a change of the loop weight. Or if we consider compare two different Potts probabilities, PAAA and PABAB, for example, which has different cluster configurations, then in such comparison, only a global amplitudes associated with the entire fine temporally leap module change, and the relation between different fields in the same module does not change. So this tells us there's some quantity that we're going to call interchiral conformal block, which organize the usual conformal fields according to the affine temporally leap module that they belong to. And it's the key point is that it's the same interchiral blocks that enter both the Potts probability and the pseudoprobability, which appears in minimal models. And so for such quantity, we can write them in terms of summing over such interchiral blocks with some amplitudes. And the name behind this is from this earlier work studying on the lattice, where they suggested there's interchiral algebra behind this logarithmic CFT, which is larger than the usual Virasoro times Virasoro bar. So one interesting result from this is that we can in fact extract some of the Potts amplitude from the well-known minimal model amplitudes. And by minimal model here, I mean the analytic continuation of the minimal models into a generic value of central charge. But the point is that such amplitudes are known analytically. So if we consider this combination, the PAAA plus the P tilde ABAB, which we just said that it corresponds to a minimal model 4-point function. And the amplitudes inside this 4-point function is known, which we call the A Liouville, since it's closely related to the C less than 1 Liouville theory. And on the other hand, each of these quantities can be expanded using these interchiral blocks with some corresponding amplitudes. And then similarly for the Potts probability combination, we can also expand them using the interchiral blocks and then write it, the coefficients given by some other amplitudes. And since we obtain many ratios of such amplitudes, we can look at these expressions. Then we manage to write some of the Potts amplitudes in terms of this A Liouville in such expressions. And to do things more systematically, we can write down the crossing equation, which under the exchange of ST channel relates these 4 probabilities in this way. And for the notations here, the superscript indicate which channel we consider. And for the subscript, it tells us which spectrum to use and what amplitudes appear here. So for example, for this third equation here, for the left-hand side, we sum over the spectrum belonging to PAABB, and then together with its amplitude, expand using the S-channel block. And on the right-hand side, we have the spectrum from ABBA with its amplitude and expand using the T-channel block. So this is a linear system of these amplitudes in these 4 probabilities associated with the entire modules. And by solving this, this way we determine these 4-point functions that we started with. And the last ingredient in this is how to write these interchiral blocks. So to do this, it's important to notice that the energy operator H21 is degenerate in the Potts spectrum, which means that its OPE with another conformal field truncate into 2 terms. And so one can study a ST crossing equation of a 4-point function involving one of these degenerate operators. And this leads to a recursion of the OP coefficients. And this kind of technique was used to solve the C less than 1 Liouville theory in these earlier works. In that case, there are 2 fields which are degenerate. One is this energy H21, and the other one is H12. And these 2 degeneracy leads to two sets of recursions of the OP coefficients when the CAC indices are shifted by 2 units. And this eventually leads to a full analytic solution of the model. But well, also this technique was also generalized to the non-diagonal case, which leads to this A Liouville that we used earlier. But in the case of Potts, we don't have this second degeneracy. So, but what we find is that using this degeneracy of the energy operator and focus on the 4-point function of the, the 4-point function of the spin operator, the degeneracy actually leads to a stronger recursion of the amplitudes when the CAC index is shifted by 1 unit, and this precisely relates different fields belonging to the same affine temporally leap module. So to write the interchiral conformal block, we sum over the fields belonging to the same module with such recursion and the usual Virasoro block, and then we can put it into the bootstrap equation to solve for the amplitudes. So here I show some of the results from the bootstrap of these amplitudes for the whole range of Q between 0 and 4. And for the red, they are the spectrum and amplitude showing up in this geometrical 4-point function. And for the blue, they are for ABAB, and green is for AABB. And these agree very well with the lattice results and also give us a very good idea about these amplitudes as a function, its analytic structure as a function of the Q variable. And we notice that there are some poles in these amplitudes at certain values of Q, which correspond to rational values of central charge. And this is expected because at rational values of central charge, the conformal blocks have poles, and which will lead to some divergence in the correlation. And so to cancel such divergence, we need some other fields with the same pole and residue. And this is exactly what these amplitudes give. And to finish, I will talk about the interesting observation from my perspective. So as we have said, for the non-diagonal C less than 1 Liouville theory, there's another field which is degenerate, and it leads to another set of recursion for the amplitudes, which in the affine temporally leap language relate the amplitudes belonging to different modules. And in that case, we also have this degeneracy of the energy operator, which both set of recursions give us a complete analytic solution of the theory. But unfortunately, this field here is not degenerate in the case of pots. But what we find, well, from observation is that there seemed to be a renormalized version of the Liouville recursion which occur in pots. So it's the ratio of the amplitudes in pots is given by the ratio, the recursion in Liouville dressed by an actual factor, which is a rational function in Q. And we get these factors either from lattice numerical calculation or by fitting the bootstrap result. But for the moment, we don't know where they're from. But the fact that such analytic function exists seems to be telling us that the model is analytically solvable. It seems important to first understand what replaces these degeneracy in the Liouville in the pots and leads to such renormalization factors, which will be very interesting to study. So to summarize, we have uncovered some interesting relations between the POTS model and the minimal models, and also determined these 4-point functions numerically through the bootstrap or semi-analytically by constructing these interchiral blocks. And one important topic that I did not cover is the logarithmic nature of the POTS CFT at generic values of central charge, which we have studied more in this recent paper. And at the same time, around the same time, there's also this other paper about the same topic. And earlier this year, there was another paper studying the ON log CFT, which is closely related to the POTS model. And some open questions important to answer in my perspective. The first is what happens at rational values of central charge, especially for Q goes to 1, the percolation limit, or Q goes to 2, describing the Ising clusters. And one of the most fascinating results that I think is what we have found about these amplitude ratios and this renormalized version of the Liouville recursion, which seem to be telling us there's a full analytic solution of the POTS model waiting for us. But to understand this, it's probably important to explore more about the symmetry aspects of the model. And I will stop here. Thank you.
Thank you very much. So questions, Alessandro? No? Oh no, that's okay. Bernardo?
Hey, thanks for the talk. I have a question. So these interchiral blocks are like
Yes.
some sum of products of Virasoro blocks. How do you get the Virasoro blocks, especially when you have logarithmic operators being exchanged?
Okay. Can you hear me?
Yep.
Okay, so for some of these modules that we talk about here, they are just the usual, they include the usual Verma modules. But for some of these, there are some logarithmic modules, so that requires some regularization of the usual Virasoro blocks. So, what I wrote here, let me see where it is. I guess I didn't write it explicitly, but when I write this sum over the recursions with the usual Virasoro block, some of the Virasoro block needs to be modified to the logarithmic block.
Right. And how do you do that? If you can explain very quickly.
So you mean just how to deal with the
How do you compute it? Yeah.
the logarithmic block? So what you can do is you take the usual OPE of the operators, and then but you focus on these conformal fields which supposed to involve some logarithmic multiplet. And then usually, I mean, what will happen is that there's a naive singularity in these OPE because what was supposed to happen is there's a null field decoupling from the theory, but for logarithmic multiplets, this null field doesn't decouple. So then you need to include some other fields to cancel such singularity, and it leads to some mixture, which will give you some Jordan block of this logarithmic structure that you want.
Okay, thank you.
Mm.
Vladimir?
It appears that I wanted to ask almost the same question about logarithmic conformal blocks. So the correct expansion will contain the derivatives of conformal blocks with respect to dimensions, yes?
That's the perspective from this other paper there. They were taking the derivative with respect to conformal dimension of the usual Virasoro block. But I personally don't understand this perspective very well. But for me, the most straightforward thing is to take the usual blocks and then cancel such singularities as what usually happen in the logarithmic CFT.
Maybe it will lead to the same.
Yeah, it should. I mean, I think we compare some of the result and it's the same.
By the way, do you know some general theory of these logarithmic conformal blocks in any dimension?
I think people suspected like pots in higher dimensions and some perhaps ON theory with n not integer is some logarithmic CFT, but I'm not completely sure.
There is a paper which describes this conformal block expansion for higher dimensional theories of Miguel Paulus.
Yeah. That's using this taking derivative with conformal dimensions perspective, yes.
You see some relation with your formalism?
I think it should be equivalent. I just personally, I'm not sure what's the meaning of taking derivative with respect to conformal dimensions, but I think it leads to the same result. I think we need to understand more what it means physically.
Okay, thank you.
Thank you.
Okay, thank you. Let's postpone further questions for the discussion session, and let's thank Yifei again for her nice talk. And maybe Ben, you can